Yep, looks good.
Okay. I see now that I don't have here access to the chronometer, to the watch. So if you then please can tell me when if I get.
Yeah, I will let you know the 30 minutes later. Okay.
Okay. Thank you. So hello everybody. I am Cristina Monteiro. I'm a researcher at the University of Coimbra, a research center called Leakage. And this work has been done in our labs in Coimbra. It is called Absolute Experimental Primary Scintillation Yield in Xenon for electrons and alpha particles. So I will say what the motivation has been for doing this work. I will present briefly the experimental setup, a gas proportional scintillation counter. I will present also the methodology that we used for data acquisition and analysis, the experimental results that we arrived to, our conclusions, and also a slide with the references of the work that is not from our authorship, and that is work that is mentioned throughout this presentation. So about motivation, we know that gaseous xenon scintillation, primary as well as secondary scintillation, is a very used parameter, or is very used phenomenon in particle physics experiments, namely and that's where we work more related to dark matter search experiments and also double beta decay experiments. We know that a very important parameter in this context is the WSC, which is its definition is the mean energy that is required to produce a scintillation photon, and this parameter is related to the primary scintillation or the prompt scintillation. So we saw that, or we noticed that in the literature, the primary scintillation yield, and in the absence of recombination, in the literature is there are a lot of values and a lot of characteristics that are scarce, dispersed, and also inconsistent. For instance, the WSC value for alpha particles is lower than the WSC value for electrons. So that is what we see in the literature, and it's not understandable. And also for gaseous xenon, the WSC value is within a very broad range. It goes from 30 eV to 120 eV. And three important features related to these values that are mentioned in the literature. It depends on the nature of the incident particle. It depends on the energy of the interacting particle, and it depends also on the electric field intensity that is applied inside our detector. So these characteristics or these features related to this WSC value are not understood, and a lot of scientists went through this and could not give an explanation, a physical explanation for this to happen. So we decided then to do a very careful, very controlled, systematic studies of the absolute primary scintillation yield in xenon gas, for X-rays and for alpha particles. And for that, we use a detector, a gas proportional scintillation counter that has been developed also in Coimbra in the 1960s. in our lab and LIP. And this gas proportional scintillation counter is a kind of laboratory size small TPC, working principle. So about the former results that I mentioned, I have here a table taken from the Nimura paper, a very known paper for who works with this this issue. And we see here that he gathered values from different authors related to the WAC value. And we see that here that they go exactly, as I said, from 30 to 120 EVs. And they are for the, and these numbers, they are all they seem related with the nature of the particle, the energy of the incident particle, and also the electric field applied. And here below, we see also other values that are not in this Nimura paper, and that also reports results for this WSC value in gas. So as you see, this is to reinforce what I said before. So about our gas proportional scintillation counter, here is a simple schematic. It has two main regions. The so-called absorption region, which is delimited by the entrance window on the upper side and by the gate grid on the lower side. And then it has an electroluminescence or scintillation region, which is delimited by the gate grid and also the anode grid. And this anode grid is placed just above the photocathode, and we used as a photosensor a 2-inch photomultiplier tube. This detector has been filled with gaseous xenon at a pressure of 1.2 bar. And we used X-rays from X-ray sources with energies between 5.9 keV and 25 keV. And we used also alpha particles of 2.3 MeV energy. And these, all of these sources, they were 1 millimeter collimated. So the gaseous xenon is inside the detector and is in a closed circuit, and it circulates and is purified continuously by hot getters from SAAS. In this detector, the signal amplification is done by a mechanism that we know as electroluminescence. So what was the methodology that we used? Here we see an example of an average waveform from, in this case, 1 million of X-ray events from the source of 14.3 keV. And here is zoomed in on the S1 signal. We see that these waveforms come as the amplitude as a function of time. Okay, and here the primary scintillation, or S1, is more than 3 orders of magnitude smaller than the S2 signal that is related with the, or that is the secondary scintillation signal. So S1 is very hard to distinguish from the electronic noise. So what we did is, for X-rays in this case, make an average waveform computed from a very high number, in this case 1 million, of events, and this is to cancel out the baseline fluctuations. For alpha particles, as the interacting energy is much higher, we can, so the S1 signal is also much stronger. We can compute the WSC value on an event per event basis, because we can see, in fact, every single waveform. So for alpha particles, we calculated AAC values by both methods, the per event basis method and the average waveform method, and this allowed us to cross-check, in fact, the waveform methods.
Cristina, you used 10 minutes, so
Okay.
3 minutes.
Yeah, okay. So what we did then was rely on the on the theoretical X-ray absorption law to make some correction on. We did a correction of the geometrical efficiency factor. We did the correction based on the baseline offsets, and we integrated the S1 between the beginning of the region and 1.5 centimeters. So I think that I said everything that is here. We triggered on the S2 rising edge on 50% of height of the S2 rising edge to then demonstrate the S1 signal. So, and here are our results for the AAC values, and you can see that they are within 40 to 50 EVs, and that is unregarding of the energy of the incident particle and also of the nature of the incident particle. In fact, it is also independent of the electric field applied to the drift region, because we varied the measurements. For the measurements, we varied the electric field between 0.1 and 0.6 kilovolt per centimeter per bar. So to conclude, the AAC value that we measured was between 40 and 50 EV. It does not depend on the nature of the interacting particle. It also does not depend on the energy of the interacting particle. Also, it does not depend on the electric field applied to the drift region. The yield estimated for the S2 yields, so for the secondary scintillation or electroluminescence yield, we did it with the same methodology, and it agreed very well with the simulations within a 5% error. So this result for S2, together with the good agreement between the average method and the per event method that we did for the alpha particles, it demonstrates that our analysis method and the geometrical efficiency simulation model that we developed are very reliable and can be applied with safety and confidence to this to this work. So here are our references, and thank you very much.
Thank you, Cristina. Nice talk. Any question or comments? Yes, Giovanni.
Hi, thank you. I'm just wondering what is the extraction field that you use between gate and anode, and if you notice any problems with having the anode so close to the PMT.
The anode, in fact, is connected to the photocathode of the photomultiplier tube with the pin.
So the PMT is a positive biased.
So, sorry, I didn't.
Sorry, I'm wondering if the PMT is positive bias. I'm just wondering if there is a electric field between the anode and the PMT.
Well, the photocathode of the PMT is at the same voltage. I don't
okay,
know.
Okay, yeah, okay.
Because
so
I cannot hear you very well, so it's.
Okay, no worries. Thank you. I think you replied.
Okay. because the sound is, you know, it's not continuous. So it's a little bit hard to understand.
Okay, thank you.
But
So
the photocathode is at the same voltage as the mesh, if that is what you are asking.
Okay, so yeah, if there's, yeah, let's continue on the chat. So let's move on to Christine. Okay, thank you. Next speaker be Sala.
Hi, can you hear me?
Yes, I can hear you.
Okay. So I will share my screen.
Please.
Okay, so hi, I'm Sara Liardini. I work in FI in Santiago de Compostela, and I'm presenting the work we did about the scintillation in xenon, also in collaboration with researchers in CMAT. So as you know, also from previous talk, xenon is a very important element in particle physics, since it's widely used for experiments that study properties of neutrinos and look for dark matter. Also because its scintillation is easier to detect than the one in argon, it has a lower background and it has a better sensitivity to WIMP mass around 100 GeVs. And it's also of paramount importance for neutrino-less double beta decay experiments, since it's the only gaseous element in which there is a natural isotope which has double beta decay. The implicit assumption of experiments so far is that the emission of xenon is monochromatic around the second continuum band that occurs in the VUV. Though there are other processes that emit in the UV visible bands and are called third continuum. And this provides a possibility to build detectors that use spectroscopic information. And a similar concept was proposed for argon in this paper, and actually also in a talk of yesterday by Vicente Pesudo. And they proposed to use the third continuum of argon to do particle ID. Other things that are unknown about xenon scintillation are, for example, the scintillation yields of the third continuum and its dependence with pressure. And this is very important because experiments that use TPCs need to know the absolute scintillation yield and the spectral content with high precision to reconstruct events. So to do so, we built our experimental setup. It's made like in this picture. So we have a cathode in which you can put a radioactive source. We used americium 241 for alphas and strontium 90 for betas. Then we have a drift region, and then a mini multi-wire proportional chamber with 4 wire planes. A gating grid, a gate, an anode, and a readout. In principle, we could connect the readout to an amplifier, but actually for this work, we operated in electroluminescence mode. And we used 4 PMTs of the same model from Hamamatsu. 2 were not filtered, so they could detect wavelengths from 145 to 600 nanometers, while 2 were provided with filters. So one could detect light from 250 to 400 nanometers. And the last one could detect light from 250 to 600 nanometers. And here I also reported the quantum efficiency of the PMTs in black as given from the data sheet from Hamamatsu, since it was useful for the further analysis. Here you can see the picture of our setup. This is one of the wire planes we used, and this is the mounted setup also with the PMTs on the top and a Teflon reflector in the drift regions. And we performed several runs with different pressures from 1 to 10 bar, different electric fields from 0 to 100 volt centimeter bar, using both the alpha and the beta source, and we took data for S1 and for S2. Here you can see the reconstruction of the spectra of the two radioactive sources. In red is the beta, and in blue is the alpha. And an example of the waveform that we were able to see with our setup. So these two that you see in the oscilloscope are the signals from the PMTs without filters, and you can see both S1 and S2. We made sure to operate in purity control conditions. During the data taking, we were circulating the gas through a getter. Between one data taking and the next one, we were always recovering the xenon and pump it from the impurities. And we performed some simulations to compare the measured drift velocities with the simulated ones. And the result was that the main contamination was nitrogen, around 300 parts per million. And as a last check, we measured the time constant of the triplet that, depending on the run, ranged between 85 and 98 nanoseconds. And this is compatible both with the estimate of contamination of nitrogen from the simulation and also with the values in literature. The value reported is 100 nanoseconds, so especially for some runs, we were in high purity conditions. As a preparatory study, we calibrated the PMTs to convert the charge into photoelectrons. So to do so, we used the 40 nanosecond pulses of a blue LED. And then we fitted the charge distribution with Gaussians, whose integral values were bounded through Poisson statistics. As a preparatory study, we also performed some simulations with Xenon-4 to estimate the light collection efficiency. Here you can see the simulated setup, and we performed simulations for both sources and for both kind of signals, so S1 and S2. Now I will show you the results of the analysis. So on the left, in the top plot, there are spectra at 0 field for different values of pressure. And well, our time window was cutting a bit the emission for the highest pressure, where there is a higher contribution of recombination, but we estimated that we missed around 5% or less. And on the bottom plot, you can see instead the spectra all at 10 bar and for different fields. And you can see that the recombination contribution disappears at higher fields. So the black one is the highest field. And on the right, we plotted the how the light changes as a function of the electric field for alphas, in which you can see that there is a strong decrease, while for betas, it remains constant, showing that there is no recombination. We also estimated the energy to produce a photon. We used this formula reported here. So we corrected the energy for the alpha, for the light collection efficiency, the transparency of the wires, and the quantum efficiency of the PMTs. And we took away from the unfiltered PMT result, the one from the filtered PMT, that is, we subtracted the contribution of the third continuum. Here you can see the results in the plot. In blue, there is the result at high field, and in red, the one at no field. And we compare them with results found in literature. in black, there is a result at high field that is perfectly compatible with our result. And in yellow, there is a result that we found at no field. And it's still compatible with the red one, but there is a systematic shift. And this could be explained by the fact that we subtracted the contribution from the third continuum, while in the work we found it was not. Here I show how we were able to isolate the third continuum contribution. And so you can see separated the second continuum in blue and the third continuum in green. And for the second continuum, you can see that at 1 bar, there is no singlet contribution, while at 10 bar, it's fully formed. We also estimated the time constants of the third continuum, and they turn out to be independent from the pressure. And the ratio of the third versus second continuum in blue is for the alphas, and in yellow is for the beta. And you can see that it's always below 10%, while, for example, in Argon, it was found to be around 20% for all the pressures. Then we calculated the yields for the third continuum. And we looked at how was the trend with respect to the electric field. And in this case, neither for alphas nor for betas, there is a decrease. So we are not seeing recombination in the third continuum. To conclude, we managed to measure the primary scintillation of xenon in purity control conditions, characterizing its time and the spectral emission for different particle types, for different fields, and for different pressures. We managed to quantify the third continuum yields that are rarely reported for noble gases. And we found that the third versus second continuum ratio is smaller than the value that was found for Argon. In the future, we will still have to analyze the data about S2 that were not reported in this presentation. And it would be also interesting to measure the third continuum in liquid instead than in gas. Thanks for your attention.
Thank you. Any question? Let's see. Hands. Any questions? So I have a question about the purity. So maybe you said, but I don't get it. You use the hot getter or?
No, we are
cold
using
getter?
a cold
Okay.
getter. So we were able to remove, for example, oxygen and water, but not nitrogen, that actually turned out to be the main contamination we had.
Okay. And you plan to use the hot getter, or do you think that this is fine?
Yeah, we were considering the idea. Actually, at the moment, we don't have a functioning hot getter. This is the reason why we didn't use it. But we should, we should make it work again. So we are considering the idea.
Okay. Okay. Thank you. Any other question to Sala? If not, let's send to Sala and then next move to next speaker, who is Florian, Mr. Florian.
Hi. I hope you can hear me.
Yep, I can hear you.
Great. And I hope you can see my slides.
Yes.
All right, good. Okay, thanks a lot. Okay, good morning, afternoon, or evening, everyone. And thank you very much for the opportunity to present our latest results here on alpha and beta interactions in liquid xenon this time. So let's dive right in. And I would like to set a stage for this measurement. So what we are interested in is to measure with our dual phase xenon time projection chamber the amount of S2 charge signal and S1 prompt scintillation signal as a function of the applied drift field. So we're going to do this using our Heidelberg Xenon or Hexe setup that you can see here. So this is our space in the lab. And as most setups, we have some slow control system to control parameters of the detector. We have a data acquisition system here in red. And we have our gas handling system in orange that allows us to recirculate the xenon and continuously purify it using this hot getter, as well as to introduce radioactive gaseous sources like radon-222 and krypton-83M. And then in green here, you can see our cryostat in which there is our liquid xenon time projection chamber. And this detector you can see in the sketch on the right. So it's filled with about 350 grams of liquid xenon here in the center. It is about 5 centimeter in height and about 5.5 centimeter in diameter. And the liquid xenon is observed by 2 PMTs with 2-inch diameter that are mounted on the top and on the bottom. The whole structure is then encapsulated in this PTFE support structure that you can see on the left-hand picture. And one special feature about this detector is this inner cylinder that is easily removable, with which we could investigate chemical cleaning recipes and their influence on the liquid xenon purity. If you're interested in this, there's the publication here linked for you. Now, as I said, we would like to measure this independence of the drift field. So one very important point is, of course, the drift field, how we quantify it. And for this, we use the COMSOL simulation of our detector that is shown here on the right. So it's a full 3D model, including all major components of the detector. And you can see we have here 3 field shaping rings along the drift axis. One electrode, one cathode electrode at the bottom, the gate electrode and an anode at the top, as well as all the 2 PMTs that we have and high voltage feed throughs that we connect our electrodes with. Our electrodes themselves are shown in the pictures in the bottom. So we have 2 versions. One is this 6 millimeter cell spacing hexagonally shaped electrode that is etched from stainless steel. And on the right is the second version, which is much finer spacing, which has 1 millimeter of pitch. And how this different pitch size affects the electric field, you can see on this slide here. In the top row, you can see a zoom in into our extraction region. So you see our top PMT here with the quartz window. Then here is our anode and our gate electrode. And here in the middle is the liquid xenon level. And if you now change from the 6 millimeter pitch grid to the 1 millimeter pitch grid to the right, you can see how the homogeneity in the extraction region is significantly improved. The same holds true for the drift region, as you can see here in the middle. So again, if you look at the field lines, for example, in red, you can see that they're much straighter in the right-hand side picture for the 1 millimeter pitched electrode. We also acquired data for both of these setups. Here in the lower line, you can see some figures showing in the left the time width of our S2 signals as a function of the drift time, so as our Z coordinate in the detector. And you can see that the distribution of the S2 width becomes much more narrow if you install these 1 millimeter pitched grids. The same holds true for the S2 size distribution, which is also much more well-defined in the right-hand side. And this is mainly due to this increased homogeneity also in the extraction region. So for the study that I will talk about now, we only use this right-hand side version. Now, I would like to talk about the data that we took. So the first source that we investigated was this krypton-83M. And just as a quick reminder, this has basically 2 decays that are time coincident. And the first one is this 32.1 kilo electron volt transition that goes via emission of an internal conversion electron. On the left, you can see how this looks like. Typically in our detector, we have this first large S1 signal. This is then followed by a short time distance of of about 150 nanoseconds by a smaller decay, by emission of 9 kiloelectron-volt, also an internal conversion electron that then yields this second S1 signal. This time delay signature makes it very easy to select these events. As you can see in the lower left, here we plot the largest S1, so this first one, as a function of the second largest S1, and the krypton events then nicely show up here and can be easily selected. And as a proof that we really see this krypton, here's the time difference between these two S1 signals that we see, and they follow a nice exponential decay with a half-life that is very well compatible with the literature value that we would expect. Now, switching the source to radon and to alpha particles, we investigated the radon 222 emission chain. So for this, we used a liquid 226 radium source from which we extracted this radon, froze it into an activated charcoal trap that we then connected to our system and flushed it into our xenon. So we expect to see 3 individual alpha decay lines, the one from radon 222, the one from polonium 218, as well as the one from polonium 214. And up here on the left, you can see how this looks like in our data. On the x-axis is the S1 signal, and on the y-axis is the S2 signal. And you can see 3 clear populations here that can be attributed to these 3 alpha emissions. Now, what we need to do is basically we need to determine the mean of these lines in S1 and in S2 for all the different fields we are studying, and then plot this as a dependence of the field. But before that, we want to determine the normalization constants. And here I show a plot that was shown yesterday already. So on the x-axis, there is the detected S1 light yield as a function of the detected S2 light yield. So we expect to see this nice anti-correlation between light and charge signal. And this is visible for example, for this krypton 83M data here in red. Just as a reminder, if we have a lower drift field, we expect to see more light because this additional recombination of charge produces more S1 signal. So we move to the lower right of this plot. If we ramp up the drift field, we can extract this charge more efficiently by the expense of S1 light. We can then fit this krypton data points with this linear function in order to determine this light yield at 0 field, which we call L0, as well as this theoretical value Q infinite, which would be the charge yield at vanishing recombination. In the insert, you can see the same for the radon alpha events. They also line up in this anti-correlation. However, as you can see, they are much more squeezed because the alpha tracks are very dense. So the recombination is very strong. Therefore, these lines are very, very steep here. Now we can plot our measurement as a function of the drift field. So here on the y-axis, you can now see this normalized yields by the normalization constants I've just shown you. So the light yield divided by the light yield at 0 field and the charge yield divided by this Q infinite value. And the charge yield is shown in red here for the krypton 83M as a function of the field. And you can see that it increases when the drift field is increased. And you can see the light yield for the 2 intermediate states of this krypton decays for the 32 kiloelectron volt and the 9.4 kiloelectron volt. And they show the opposite behavior. They are decreasing with the increasing drift field. You can also see a reference measurement from literature that is quite well in agreement with our data. And you can see this dotted black line that is a fit to our data with this modified Thomas-Emmett box model that is shown down here. What is new about this measurement are now the field values, the measurement here at very low fields, smaller than about 100 volt per centimeter. Now we can do the same for the radon data. This is shown here. Now you have to keep in mind that this y-axis is broken and the total range is only about 5%. So for the light yield on the top, you can see that we also see a slight decrease of the light yield with increasing field strength that is kind of compatible given our error bars with the literature measurement. For the charge yield down here, we also see that this is slightly increasing with the applied drift field. However, here we see a significant difference between our results and the ones from the literature. that is currently still under investigation, and I would be happy to discuss this about. As a secondary measurement, we also can determine the drift velocity of electrons in liquid xenon, and this is shown in this figure. On the x-axis is the drift field, now on a logarithmic scale. On the y-axis, the drift velocity of electrons in liquid xenon, measured at a liquid xenon temperature of 174 degrees. In black, you can see our data points, and they are fit with this function here that is just the sum of two exponentials, which is inspired by the NEST framework, where it's also modeled like this. New about this measurement is now that we have measured the drift velocity down to quite low fields at 7.5 volt per centimeter, and ranging up to drift fields as high as 1.6 kilovolt per centimeter. This brings me to my summary. So I hope I could have convinced you that in our TBC, we have improved our field homogeneity by using this 1 millimeter pitched electrodes, and that we have a quite good understanding of our field and the uncertainty using this detailed 3D model. I've shown the results in a drift range from 7.5 volt per centimeter up to 1.6 kilovolt per centimeter. And I showed results for the LIDINE charge yield of radon-222 alpha particles and krypton decays. And we will have a publication on this very soon. So stay tuned, and thank you very much for your attention.
Thank you. Any question? Oh, many hands. First, Austin.
Hi, thanks. That was thank you for the great talk. So I had a question about, I guess, this plot shown in the bottom right, where there's this discrepancy in the charge yield as we go to infinity. Have you accounted for the ratio of excitations? Because those don't contribute, like you're not going to get charge from those, even though they'll make light. Could that explain this discrepancy?
So for this figure, we just normalized using basically the method, method shown here, basically. So we extrapolated this line up to the point where it's intersecting with the y-axis, and there's no contribution from this considered now. So this could, of course, be a difference.
Yeah, because some people have those values as high as 10%. So then that would, you would basically need to take the y-axis value not at x equals 0. So maybe that could explain it.
Okay. So maybe another idea that we had is that the normalization that was done in the reference measurement was done in a slightly different way. So it was not by this anti-correlation, but by taking the alpha emission energy dividing by the work function. And but we can have a look into this. Yeah, thanks.
Brian?
Yeah, thank you for the very nice talk. My question is about the alphas. Do you have any plans to measure the like intrinsic resolution of alphas in liquid xenon, in the charge and the light?
So what I can tell you basically is the resolution we observe here in these CS1 and CS2 space. This is about 5 and 4% for CS1 and CS2. However, I think that this is limited by our detector and not by the intrinsic resolution, since we do not have any XY position information of the events, so we cannot correct for the XY dependence of the light collection efficiency, just for the C dependence, and the S2 we just correct for the electron lifetime. Probably with our instrument we cannot reach the necessary resolution for doing this. Did I understand the question correct?
Yeah, absolutely. Thanks very much. And again, very nice work.
Thanks.
Thank you. I have actually the one question on slide 8. So you have an anti-correlation from a krypton and then alphas. Those anti-correlation, the slope, do they agree?
This is a very good question. Thank you. So for the alphas, let me quickly jump to this slide here. For the alphas, we have to do a small trick to measure because they are so bright that they would saturate our PMTs quite strongly. So we place thin PTFE attenuators in front in order to attenuate the light to measure it correctly. So for this, we also did a measurement, and also colleagues in Münster did a measurement. There are some publications if you need these values. So the detection efficiency for photons in the two measurements from krypton and alphas cannot be compared directly due to the presence of these attenuators. So the slopes are not comparable.
Okay, but there's still this analysis itself is varied.
Yes, because we determined this anti-correlation. Sorry, for normalizing the yields, we just take the Q infinite and L0 from this anti-correlation. So this should still be correct.
Okay. Thank you so much. Thank you. If there is no more question, let's move on to next speaker. Christoph.
Yes. Okay, so do you see my slides?
Yes.
Okay, perfect. So thanks for having me today. I'm Christoph Vogel. I'm a master's student at TU Munich, and I'm happy to present our recent results on Xenon-Doped liquid argon here on this conference. Let me start by reminding you that liquid argon is a widely employed scintillation and shielding medium. It has some very nice properties for rare event searches. For example, it has a high light yield, a high stopping power, and an excellent pulse shape discrimination performance. And all this comes at a reasonably low cost. However, there are also some imperfections, some challenges which come with liquid argon. For example, its VUV emission wavelength is only 128 nanometers long. This makes the photons difficult to detect. Commercial photodetectors have a low detection efficiency at this low wavelength, and often wavelength shifters are used which have their own challenges. Liquid argon has a long scintillation time. Its triplet lifetime is about 1.3 microseconds in pure argon, which leads to long signal windows. And together with the high specific argon-39 activity in commercial argon, which is atmospheric argon of about 1 becquerel per kilogram, this can lead to large detector dead times in large volumes. Also, liquid argon features a rather short attenuation length of about 1 meter. So the scattering length is about 1 meter, and then there is the absorption length, which is impurity dependent. This limits the maximum distance between the photodetection system and the light the interaction point of the ionizing radiation. And in general, it limits your detector size. Xenon doping improves the scintillation and optical properties of liquid argon. This is due to nice properties of liquid xenon scintillators. They feature a longer emission wavelength of 175 nanometers and a shorter triplet lifetime of only 20 nanoseconds. However, this substance comes at a much higher price. So combining liquid argon with xenon results in so-called xenon-doped liquid argon, where only small amounts of xenon are used. It has the properties of a longer emission wavelength, a shorter triplet lifetime, and a longer attenuation length than liquid argon. The longer attenuation length is mostly due to less scattering because of Rayleigh scattering. Also, it's very cost efficient compared to pure liquid xenon. The technology of xenon-doped liquid argon has been investigated in the last decades very thoroughly. I included a small list here at the left bottom. However, there are still some unresolved issues. Previous work measured the only subsets of the important parameters, the relative light yield, the effective triplet lifetime, and the effective attenuation length at a time. It's also important to perform a simultaneous measurement. Also, typically moderate volumes between 30 milliliters and 100 liters were investigated in the past. Of course, since yesterday's presentation, this point should be updated. No measurement of the actual xenon concentration in the liquid phase has been performed in these experiments. This is a very important point because the doping process, so actually putting xenon into the liquid argon, is not so trivial. You can have losses there. And I don't mean that you forget to close a valve and you lose some gas. I mean that xenon is solid at liquid argon temperatures. And therefore, it can freeze to the cooling coils of the cryostat or the cryostat walls or somewhere else. In this talk, I will present our measurements of the scintillation of Xenon-Doped liquid argon, where we performed simultaneous measurements of the effective photoelectron yield, the triplet lifetime, and the attenuation lengths at xenon concentrations ranging from 3 to 300 parts per million by weight. We performed these measurements in a large mass of about 1 ton, and we had the possibility with a mass spectrometer to measure the actual xenon concentration both in the liquid and in the gas phase. Next, I will present our experimental setup. So this is a piping and instrumentation diagram of our mixing process. Before injection, xenon is diluted with argon. This is again due to freezing and cluster formation, which could happen if pure xenon is used. We take xenon 5.0 and mix it together with argon 6.0 in an external mix bottle. We dilute it heavily and then inject it into our cryostat SCARF, the subterranean cryogenic argon facility at TUM, directly into the gas phase. In the gas phase, it condenses then by itself into the liquid phase. Then, after injection, we can take samples just easily by a valve and a pipe from the gas phase to EDIFIX, the impurity detector for investigation of xenon, which is our quadrupole mass spectrometer system, but also from the liquid phase. Taking samples from the liquid phase is more challenging, but we found out that when a pre-vacuum pump is used to actually pump directly the liquid phase, and this for several cycles, the xenon concentration in the gas phase is the same as in the liquid phase. So the phase transition in this so-called forced evaporation mode is retained throughout the phase transition. The scintillation is observed by a triggered SciPM array by LAMA, the Legend liquid argon monitoring apparatus, which is able to measure simultaneously the relative photoelectron yield, the effective triplet lifetime, and the effective attenuation length. So LAMA is this about 85 centimeter large construct, which features 16 VUV sensitive SciPMs. These are Hamamatsu VUV4 SciPMs, which are located at different distances from the light source. The light source is this copper object in the bottom. It features a radioactive americium-241 source emitting 60 keV gammas, which induce scintillation. The 3 source SciPMs, which are placed directly here, are only 1 centimeter away from the interaction point and allow us to obtain the relative photoelectron yield with not having to worry about any attenuation effects. The first peripheral SciPM is giving us, together with the source, the timing information. And all SciPMs, the peripheral ones together, allow us to determine the attenuation length. Now let's come to the results. The measured xenon concentrations in the liquid phase do match the target values. First, the investigated xenon concentrations were actually 0, so pure argon at first, then 3, 10, 50, 100, and 300 parts per million by mass. For 50 ppm and above, mass spectrometer data is available for the liquid phase. Before this, unfortunately, the experimental method was not yet mature. As you can see, for 50 and 100 ppm, the measured xenon concentration is somewhat lower than the target value. This is attributed to a loss through continuous measurements from the gaseous phase during the xenon condensation into the liquid phase. This was noticed and resolved at 300 ppm target concentration, which is the reason why here this systematic underdoping is not present. The uncertainties of these measurements are dominated by the 5% repeatability uncertainty of the used vacuum gauge. Here, I want to show you that the properties of xenon-doped liquid argon change immediately after xenon-argon mixture injection. So first, in the top plot, you can see the xenon concentration in the gas phase of our cryostat. And on the x-axis are hours after injection. So we start with a very high xenon concentration in the gas phase, and then it goes down very rapidly. This is condensation, and you can directly see the transition into the liquid phase. At the same time, you can see the change in effective triplet lifetime. It decreases, and the increase in relative photoelectron yield. You can also see that mixing does take a couple of 10 hours before it's really stable. This interruption here is due to a different measurement taken at that time, but you can see that after the interruption, approximately the curve follows where it first stopped. If we zoom out of this plot, I can show you all of the continuous data we took over several weeks. So each of the colored region here is one of the target xenon concentrations. And you can see in general that the relative photoelectron yield increases, the effective triplet lifetime decreases, and the attenuation length increases as expected. However, at 3 parts per million, we observed, and we believe this is to the first time, a very peculiar effect. The photoelectron yield decreases, whereas the effective triplet lifetime increases. This is still currently under study. In the last 6 days, we observed the mixture without changing it and can now demonstrate stable parameters over these 6 days in the 300 ppm time frame. The stable phases of all of these time frames were averaged to have very high statistics and yield our final values of the relative photoelectron yield and other parameters. So quantitatively, we can say that the photoelectron yield approximately doubles. However, this is due to a large part of this increase is due to the increased photo detection efficiency of the VOV4 CPMs at the xenon wavelength. The effective triplet lifetime decreases very much. It decreases by a factor of 10, and the effective attenuation length increases by a factor of more than 10 to over 6 meters. These effects saturate at the highest concentrations at a few hundred ppm, which is as expected from past literature. Let me conclude this talk by a summary. Xenon doping can improve the liquid argon scintillation optical properties for specific applications. In this talk, I presented a characterization campaign of the scintillation properties of xenon-doped liquid argon between 3 and 300 ppm xenon concentrations. We measured the relative photoelectron yield, effective triplet lifetime, and attenuation length simultaneously in a single setup. Additionally, the actual xenon concentration was determined in the gas and in the liquid phase and confirmed successful doping. We observed strong effects, which I presented before. We also demonstrated stable optical properties at the highest concentration for 6 days. These measurements were performed as part of an R&D program for Legend, where we envisioned to minimize the dead time and maximize the instrumented liquid argon volume. Future work will be carried out as well. We are going to determine the absolute photon yield of xenon-doped liquid argon and perform a real long-term stability demonstration of this technology, meaning in the time scale of months. Thank you.
Thank you. Any question, David? Sorry.
Hey, Christoph, nice talk. I'm wondering if you go back to the slide where you show the different parameters that you measured over time.
This one?
Yeah. Why is the triplet lifetime so short at the start of your run?
Yes, it's a bit lower than 1 microsecond. It is low because we had some impurities in the cryostat, so some atmospheric inflow.
Okay, so the argon started off already impure.
Yes.
Okay.
Nico?
Thanks.
Sure.
Nico?
Hi, nice talk. Thank you. I have 2 questions. First, do you have any explanation from the point of view of the, say, scintillation model for the increase of the light? And second, how did you calibrate the photoelectrons? Thank you.
So for the first question, this is a bit difficult because this is still under study. So I cannot really comment on the decrease here. Or do you mean the increase? Sorry, again, of the photoelectron yield.
The increase.
Ah, the increase. Okay. Yeah, the increase is partly due to the increased photo detection efficiency of the VOV4 CPMs, but this doesn't explain everything. There is also the fact, which was the question before, that the argon was not perfectly pure in the beginning, and the xenon is recovering some of the lost light due to impurity quenching. Does this answer the first question?
Yes, thank you.
Okay. For the second question, maybe Mario Schwarz can answer this in more detail. He did these measurements together and is the expert on the IPMs here in this project.
So about the calibration of the IPMs, I mean, they are done permanently and adjust from the spectra we get. So we get the spectrum with 1, 2, 3 photoelectrons, and always they are permanently corrected or permanently calibrated. So we always know where the 1, 2, 3 PE peaks are.
Okay, thank you.
Okay, so any other question? I have one question, but maybe we don't have a time. I have a question about the purification system, but let's discuss on chat.
Okay, so here was no purification performed.
Okay, so okay, and okay, thank you. Denver, could you answer in the chat?
Sure.
Thank you. Let's move on to next speaker, Battery.
Hey everyone, thanks for having me. Cool. Okay. So, hey everyone, and I'm just going to assume that my microphone is working, and if not, just let me know. So, thanks for having me. My name is Vetri. I'm a PhD candidate at UC Berkeley, and I'm going to be telling you about an analysis that I've been leading on electron versus nuclear recoil discrimination in liquid xenon with an experiment we call PIXI. So PIXI is an R&D scale xenon two-phase liquid gas TPC, which was operated at Yale in 2014 to 2016. So it's a lot smaller than an experiment like LZ or Xenon N-ton. It's about a 3 kilogram liquid xenon active volume. But what that allows us to do, right, is it allows us to study the dynamics of liquid xenon TPCs. And so we've completed, and there are ongoing analyses on different types of calibrations, electron extraction efficiency, single electron backgrounds, and signal background discrimination. And it's the latter that I'm going to be telling you about today. Since I'm the first TPC talk, I know most of you all know about this. I think I'm the first liquid gas TPC. Just a quick reminder, you have an interaction in the liquid xenon bulk, which is kind of in the center in this image. Photons are created, they're detected by the PMTs, and electrons are created, drifted through an electric field, produce secondary light in the gas, and that's what we call the S2 signal. So just so everyone's on the same page. So you know, as we're moving forward, this technology is used by lots of experiments, in particular dark matter searches. And the dominant backgrounds for WIMP dark matter searches in the coming years, the signal is a nuclear recoil, and the dominant backgrounds are electron recoils, which are shown here. So they're from things like radon and its daughters, solar neutrino scattering, neutrino full double beta decay, and detector and surface backgrounds. And these are all ERs. And so as a result, and then they're, you know, intrinsic to the xenon. So you face these backgrounds that can't be eliminated by shielding and fiducialization because they're just in the center of xenon volume. So the only thing you can do is to discriminate the electron versus the nuclear recoils. And as a reminder of how to do that, remember that this is the picture of how energy is deposited in liquid xenon. The key thing to realize here, it's a GIF that goes back and forth between ER and NR. The key thing to realize here is that the original ratio between the number of excitons created and the number of ions created for a single recoil, that ratio varies for ERs and NRs. And in fact, the heat percentage, right, the amount of energy going to heat, that varies too. And so this ratio of the detected charge to the detected light is a discriminating factor. So let me get into the actual meat of the analysis, because I think that's all review for most people here. what we do in this experiment and in a lot of experiments is that we discriminate ERs, electron recoils, from NRs, nuclear recoils, by using the ratio of charge to light produced by the recoil. And in practice, that variable, that ratio is log 10 of S2 over S1. And in Pixie, right, we have calibrations for ER and NR that allow us to study discrimination as a function of detector parameters like drift field and energy. And then that allows us, right, to inform future detectors to understand what fields they should be operating at, what energy range for different dark matter searches are interesting. And so great. So for today, the detector parameters and data parameters for this analysis that I'm looking at, the data has been collected with only single scatter recoils isolated. So that's one S1 pulse followed by one S2 pulse in some reasonable time window. Additional cuts have been applied for quality and fiducial volume selection. There's an extraction gas field of 8 kilovolts per centimeter, which corresponds to an extraction efficiency of somewhere like 75% or so. For today, I'm going to be presenting data on 2 drift fields, so 117 and 213 volts per centimeter. And the G1 and G2 are about 0.11 photoelectrons per photon created and 30.2 photoelectrons per escaped electron. So before I show you like the discrimination results, let me just tell you about the calibrations first. So for ERs, we calibrate with sodium-22, which is a gamma source, of course, and we tag the recoils with an external sodium iodide detector. So the events are very clean because we know that the collision in the xenon and the collision in the sodium iodide happen at the same time. And this, by the way, the energy spectrum from this is about flat, although we do adjust for that for any imperfection, but it's roughly flat. For nuclear recoils, we use a DD generator. So that is generating 2.5 MeV monoenergetic neutrons from deuterium fusion. That is a recoil spectrum. Although the neutrons are monoenergetic more or less, the recoil spectrum corresponds to about a 60 GeV WIM. So it goes up to about 70-ish keV NR. And for calibration of our detector, we use krypton, which is a 2-step decay, right, depositing 32 and 9 keV conversion electrons. That's dissolved in the liquid xenon, so recoils uniformly fill the detector. And this, of course, allows us to identify clean monogenetic signals and characterize position-dependent and field-dependent phenomena. And I have some backups if you want to talk about that, but I'm going to move past that for the moment. So this is like the interesting stuff. So the electron recoil band looks something like this. So on the x-axis is the light signal, S1. On the y-axis is this discriminating ratio, log 10 of S2 over S1. The C, right, just means it's position corrected. And you see that it forms this band of events with some center and some width. And so what we do, right, is we split the events into bins of S1, C, and then the distribution of log S2 over S1 is fit to a Gaussian, and the ER band median and width, 1 sigma width, are extracted. And by the way, this distribution is technically skewed. It's not a perfect Gaussian, but I'm going to ignore that for the moment because of just because of some limitations at the moment, but working right on for the future. The NR band is a similar story, but these are just for nuclear recoil events. Note, right, that the events are very biased towards low energy, which is consistent with it being similar to a WIM spectrum, whereas the ER was flatter in energy. Putting these two together, this is the central piece of the story that we really want to know. So if you extrapolate the ER band Gaussian fit below the NR band, then you can calculate leakage fraction. I should have pointed this out earlier. These two plots look like they're the same, but the y-axis is different, right? So the NR band is below the ER band because the y-axis is changing. So okay, so you can extrapolate and calculate the leakage fraction. This is at 50% NR acceptance. And the leakage improves dramatically with energy, as seen by others, notably Lux. So, you know, below 50 photoelectrons or so, there is some, you know, behavior that it varies as a function of energy. And this is real. This isn't just a statistical fluke, but above 50 volts, 50 photoelectrons, the leakage drops down dramatically. So that's great. And the top here is showing the equivalent nuclear recoil energy. So, you know, as you get to S1 of 100 photoelectrons, you're getting less than 10 to the minus 6, probably, you know, there's some error bars here, but something like 10 to the minus 6 leakage at 100 photoelectrons, which is about 72 kVNR. And by the way, the leakage over the entire WIMP search region, which I'm just estimating as 0 to 80 photoelectrons, that should say, I'm sorry, that's a typo, that should say PHE for photoelectrons. That is about 1 times 10 to the minus 3, which is substantially better than the LZ requirement of 5, and it's substantially better than most, how do I say, most of the notions that people have in their mind for Xenon detectors. There's this 99.5% number that's often cited, but it's you know, it's substantially better than that. Now, if I compare this, by the way, to Lux, which operated at a similar drift field and similar G1, then I get similar results, which is fantastic. This is the ER median, the ER width, the NR median, and the NR width versus S1 for Pixie, green, and Lux and magenta. And they're pretty good comparisons. It's a little bit lower in Lux. The ER band median and bandwidth are a little bit lower, but that makes sense because of the higher G1 and the lower field. Similar story with NR, except the field doesn't matter so much with NR, but the G1 will make a bit of an impact. The other thing to point out is the ER width is much higher in my measurements than in Lux, but that's because of this skewness thing I mentioned a moment ago. I'm not using a skew distribution, but Lux did. And if you use the form of width that is appropriate for a skewness distribution, just the definition of that is going to be lower. It's called sigma minus in the Lux paper. But overall it matches with Lux, so that's great. And by the way, it matches with Nest too, right? So there's this simulation package Nest. Hopefully most of you have heard of it. There's a talk this afternoon if you haven't. If you compare the Pixie measurements in green to Lux and Nest, again, yeah, a fantastic measurement. Fantastic agreement. So that's really excellent. By the way, this has all been done at 200 volts per centimeter. Let's say we change this to 100 volts per centimeter. Similar story. I'm just showing the leakage right now, but again, matches Nest. Of course, there are much larger statistical uncertainties on the Pixie data, which we are working to drill those down and make those smaller. So that's, you know, stay tuned. But for the moment, the comparison is quite good. And let me kind of conclude by showing this plot. So this is kind of the thing we really want to know. So stepping back for a moment from this result and looking at the bigger picture, right? Experiments like Xenon, Anton, and Lux, and LZ, and maybe like Darwin or something of that nature, need to decide, you know, what field do you want to operate at? Because like, it's hard to operate at high fields over such a massive drift length. But at the same time, you know, you don't want to lose sensitivity because of that decision. And so even though there have been experiments that have operated at the kilovolt per centimeter region, including Pixie, which I don't have today, but we are working on it. You know, understanding how the discrimination varies as a function of field is really critical. So this is a plot overlaying some Lux data in magenta, Xenon 100 data in black, and this work in Pixie in green. And what you see is that the Pixie error bars are pretty substantial right now, and we're working on it. But at least the centroid matches the Lux behavior really, really well. And even if you consider the statistical uncertainties, that it's matching well, and it is at least consistent with showing how the leakage is varying as a function of this field choice. So let me just conclude by saying that, the PIXI experiment has demonstrated robust discrimination at high energies, achieving a factor of 10 to the 6th or so at S1 of 100 photoelectrons, 70 keV/R, consistent with past experiments, including Lux and Xenon 100. We're working on focusing on the ER skewness, further variation of the drift field up to kilovolt per centimeter fields, and reducing measurement uncertainties. So that's all I have for today. Happy to take questions if there are any.
Thank you. Any questions? So I have one actually. So I thought that this distribution skewness is important to calculate the leakage. Is it? No?
It is. And so it's, the skewness, you're correct. So the skewness is, let's look at this, I guess. The skewness is, let's look at this. The skewness of the ER band is positive, right? Which means that events are biased higher than they would be with a Gaussian. So the skewness helps you and provides you better leakage. So the results that I'm showing are, you're correct, because I don't use a skewness, they're a bit conservative actually. So the leakage is actually better than what I'm showing. But I just don't have those fits right now.
Okay, thank you. Fabian?
Yes, thank you a lot for this very nice talk and comparison you showed. If you could go to slide 9, I think it is, you've shown your leakage fraction and attributed to both the corrected S1 and the energy, which of course assumes a certain G1 of your detector. Now, imagine if you have a better photo detector, better, I don't know, quantum efficiency or so, could double your G1. Do we have an understanding whether the fluctuations here that lead to a leakage are mainly due to the primary processes fluctuation or to the detection?
No, great, excellent. So the primary, the primary source of fluctuations for discrimination is the recombination fluctuations. And so those are going to be, the recombination fluctuations of electron recoils. And so if you have like a better G1, then the scaling between S1 and energy is going to change. And so I think it's going to be closer to scaling with S1. Like I think if you have a better G1, I think the discrimination versus S1 will stay constant, I believe, and the discrimination versus energy will improve.
Okay, which means better G1 would allow us to move the 30 kV, which we have here, up to 7 to 60 photoelectrons detected or so, and by that we could reach a higher discrimination as well.
Yes, exactly.
Thanks.
Okay, thank you. So let's move on to next speaker, Lion.
Okay, hello, I'm Ryan Smith. I'll be discussing some light yield measurements and superfluid helium-4 on behalf of the SPICE Herald collaboration. So SPICE Herald is a group of about 40 people across 8 institutes that are working on the Tesseract project, which envisions a set of different low mass dark matter detectors, which are tied together by their TES readout. And Herald would be a superfluid helium cell, which is surrounded on all sides by calorimeters. So you get about 4 pi coverage and good detection efficiency. And we'd be looking at a number of different signals in the superfluid. Those can be phonons and rotons, which we mostly detect through quantum evaporation at the superfluid surface. They can be photons, which is going to be the main focus of this talk, and long-lived triplet excimers, which we expect to detect directly through their quenching onto the calorimeters. And you can hear more about Herald in detail from Roger. He'll be talking about it today at 11:15. For today, the main point you need to know about Herald is that it expects to have discrimination power between electronic and nuclear recoils through the ratio of those different signals. And particularly, it relies on a predicted large scintillation yield in superfluid helium-4 down to low energies. So we think we could get good discrimination power well below 100 eV or so. And that high scintillation yield, you can think of as being a good Lindhard factor, but it's not something that's been measured yet to low energy nuclear recoils. So today I'll present some step in that direction. The setup we took these measurements with is a 1-inch cell of superfluid helium at 1.75 Kelvin, and it's surrounded on all sides by 6 PMTs, making a cube. And that gives us a good collection efficiency. And we expose the cell to a gamma or neutron source and tag the outgoing gamma or neutron using a far side detector to resolve the recoil angle and therefore the recoil energy in the superfluid helium. For electron recoil data, we used a cesium-137 source, and we tagged the outgoing gammas with a sodium iodide far side detector. And there's a couple cuts we make on our vents here. On the left-hand side, you can see the distribution of energies deposited in the sodium iodide. And you can see the result of a coincidence cut between the sodium iodide and superfluid signals. And that mostly serves to remove these events where actually the gamma had its full energy in the sodium iodide. So these are accidental coincidences that gamma didn't actually scatter in the superfluid. The coincidence cut removes a lot of those, so you get the orange distribution, which we then cut on the energy deposited in the sodium iodide. So we expect the 661 keV minus the recoil energy to show up in the sodium iodide. In this case, the recoil energy for this data set was 185 keV. And so we cut around that. And you can see the result of that on the distribution of signal sizes in the superfluid helium. We take that distribution of signal sizes and we fit it to a Monte Carlo made in Xenon-4 of our setup. We're floating the width and the scaling both in X and Y here. On a per data set basis, we calibrate this x-axis of photoelectrons using a delayed scintillation signal that's mostly single photons. And so that allows us to monitor for changing PMT gains over time. Looking across all of our electron recoil data sets, we expect there to be a light signal that's just proportional to the energy deposit in the superfluid helium-4. And our data is consistent with that. And we're detecting a mean of over 1 photon per keV. If you look at previous experiments, let me know if you have an experiment that you know of that exceeds this, but as far as I can tell, the largest previous light yield was 0.07 photons per keV, much smaller, because previous experiments have been focused on higher energies and not emphasizing the high detection efficiency to get to lower energies. So we'll use that mean light yield number as a baseline so you compare the nuclear recoil light yield to. For nuclear recoils, we use a DD neutron generator and we tag the outgoing neutrons with a liquid scintillator far side detector. Similarly to the coincidence cut in sodium iodide, we cut our data by the time of flight between the superfluid signal and the signal in the liquid scintillator. And then additionally, in the liquid scintillator, we have pulse shape discrimination that allows us to cut out gamma events. So that you can see that in these 2 bands on the lower left-hand plot. And then again, we fit to Xenon-4 simulation. In both the ER and NR case, we're fitting only within this green window. That's a bootstrapped fit window. That's because we see in some data sets an excess at small yields that isn't well captured in the simulation and we don't fully understand. As well as looking at the total scintillation yield in nuclear recoils and electron recoils, we can look at the timing of that scintillation. So the scintillation itself has multiple components, and in previous literature, it's been identified that in addition to the prompt pulse, you can see that in these first bins, there are exponential and power law decaying components of the scintillation. So that's this decaying elevated rate of single photons after the prompt pulse in our event window. And we fit that decaying distribution to an exponential and a power law. The 1/T power law here is expected to be due to triplet quenching. The exponential has been previously reported in the literature at a similar lifetime to what we get from our fits, but it's not as well understood. It could be a excited atomic state, metastable atomic state that is being quenched by neutral helium, but that's more of a hypothesis. It's not as well understood. Before I look at the data across all our recoil energies, I'll briefly describe the model that we'll compare to. So in the model, it sort of breaks into two parts. There's a prompt model, which is represented by this plot on the right, and that uses Lindhard, as well as measured atomic cross sections and some measurements at higher energies that are extrapolated down to predict the number of singlet and triplet excimers that we get at short times. So in the end, it gets to this solid green curve for the number of singlets we see, and that'll predict our prompt scintillation signal. And then in this paper we've extended that model to account for the 1/2T scintillation as well by feeding the number of triplets from the prompt model into triplet quenching model following King and Volt's predicting triplet quenching in diffusion dominated cylindrical tracks. So most of the parameters in that equation, that's this equation down here, are from the literature. We feed in our initial number of triplets from our prompt model, and then the model uncertainty mostly comes from this parameter KF, which represents the probability that when two triplets quench, they will form a singlet, which then scintillates. So our model prediction ends up being this pink band at the bottom. Here's our first data of nuclear recoils down at these the sort of 100 keV scale. And you can see that this data is relatively close to our predictions. And in particular, there's a good fraction of the recoil energy that shows up in scintillation. I tried to compile some rough numbers from other scintillators to compare to here in terms of the relative light yield and the fraction of energy in scintillation. And you can see that superfluid helium at these energies is either similar to or greater than these numbers for other scintillators. And we only expect that comparison to become more favorable towards lower energies where the favorable Lindhard factor for the lighter mass wins out. So ultimately, Harold wants to be able to look at lower recoil energies than this. So we'll be pushing to get data towards lower energies that I'm showing in this plot. And we can also look at how the partitioning of the scintillation among those different times components compares across energies and across electron and nuclear recoils. And you can compare these data points to the model bands. That gives some handle on how well we're modeling the populations of excimers in the superfluid. And in addition, you can see that in the electron recoil case, there's a larger prompt fraction than the nuclear recoil case. That's mostly coming from a smaller 1/T component because of less triplet quenching. It's less density of triplets in the electron recoil case. And that indicates that in the scintillation signal alone, you can have some discrimination power between electron and nuclear recoils at this energy scale. So as I mentioned, we want to be looking at even lower energy nuclear recoils than we've achieved here. We think we can get down to about the 50 keV, that's our lowest data point here, to about 10 keV with essentially the same setup we had 2 of our PMTs not functioning during this first run, and the other PMTs didn't have as high gain as we would have liked. So by resolving those issues, we think we can push down towards 10 keV nuclear recoils. And to go lower than 10 keV nuclear recoils, there's a couple changes we would make to our setup. One is that you can see this in this plot on the left-hand side, that if you're using 2.8 MeV neutrons from a DD generator, you need to look at pretty small recoil angles to get to less than 10 keV recoil energy. And so it becomes more practical to start off with lower energy neutrons. And to that end, we're developing a antimony beryllium 24 keV photoneutron source. In this picture on the right, you can see that shielded source being characterized. And in addition to using different neutrons, we would move towards replacing the PMTs with a TES readout. And that give us a big boost in the quantum efficiency, where it's close to 100% for transition edge sensors versus about 15% for these PMTs that we're using. And so that'll give us a lot more sensitivity to small signal sizes in the superfluid. Thank you. That's the conclusion.
Thank you.
Any questions?
Yep. Diego?
Thank you. Amazing talk. I have a very stupid question. Is there any possibility to dope helium with xenon to try to recover part of the energy from the triplet and avoiding TPV? I mean, I guess you have considered this somehow. What are your thoughts?
I'm not aware of work towards that. I guess it'd be challenging because this is superfluid helium. It's very cold. The helium would, or the xenon would freeze out, right? So I think that would be a challenge for that.
Yeah, it's cold at the temperature of liquid argon too, right? It's 100 degrees below the freezing point of xenon.
Right, but despite that, the xenon actually does dissolve in the argon. That would not be the case.
Maybe yes, maybe not.
Yeah, no, density might be too different.
Yeah. Yeah, it doesn't look easy at all. But
the xenon actually does dissolve in the argon. It's different chemically than the case of xenon and helium, where it'll freeze out.
Why?
Actually, if you're on my next talk, I'll cover exactly why this is.
Good. Thank you. I have just one quick question. Do you have a timeline to switch to TES?
I don't know that timeline off the top of my head. We're hoping for this run with resolved PMT issues sometime in the coming months or so. But TSs, I guess I would hope that we might be able to move towards that in the next year.
Detectors being tested now. We'll see.
Okay, thank you. Yeah. Okay, so let's move on to our next speaker. Ethan?
Yes, thank you. You seeing the screen?
Yes.
All right, outstanding. Thank you. So my name is Ethan Bernard. I'm from Lawrence Livermore National Laboratory, and I'm going to tell you about doping two-phase liquid argon detectors with xenon to improve their S2 response. Okay. So the motivation is, as you all know, single-phase liquid argon is like the workhorse target medium for a lot of low cross-section physics, and we have several great working examples of machines operating very well, and we've heard about some of them in this conference. But if you're paying attention, you'll notice that at the lowest energy scales, for the lowest energy events, dual-phase xenon is still the most successful target medium as opposed to dual-phase argon. And xenon has really done spectacularly well in the last couple decades, with now electronic recoils in xenon resolved all the way down to 186 electron volts. And nuclear recoil yield has been measured all the way down to, this is ionization yield, measured all the way to 300 electron volts, which is about where a single ionization electron is produced by the xenon. And there isn't comparable performance yet from dual-phase argon detectors. And the reason for that is that the light produced in the S2 signal is much more difficult to detect in the Argon detector relative to the Xenon detector. And that's because the light is coming out at this inconveniently short 128 nanometer wavelength. And it is also coming out over an inconveniently large amount of time. It's typically several microseconds for an S2 signal. And that light has to be wavelength shifted before it can be detected by whatever photo detector. And that wavelength shifter, that provides opportunities for energy loss and most significantly provides lots of opportunities for fluctuation in the amount of photons that are passed on to the light detector. And so we'd really like to make Argon more Xenon-like because there's features of Argon that we really desire. In particularly, it's a lighter target, and so it's a better match to light particles. And of course, Argon is much cheaper than Xenon. So our project is to make Argon more like Xenon in its S2 response. And just to illustrate that point, here's a couple of spectra of the, this is the low energy S2 spectra. On the left is a liquid argon detector. That's the dark side 50 detector. And so here you can see the single electron, single extracted electron curve coming out, going toward the anode. Here's the S2 from a single electron in the blue curve. And then from 2 electrons coming out, that's the red curve. A lot of overlap between those. On the right is the Xenon detector. This is a small detector called Xenu that was used at Livermore. And you can see that there is the much finer structure and better energy resolution that allows those electrons to be resolved very well. Also notice that in the Xenon detector, there's a lot more electrons, there are a lot more photons collected in the light detector for each extracted electron, about 3 times as many. And the comparison between these two is actually a bit misleading. The difference between these technologies is actually even greater than suggested by these 2 graphs. And that's because the dark side 50 experiment over here, that is, its photodetectors are seeing the S2 light with a larger solid angle relative to the Xenon detector on the right. So there's a lot of room for improvement in the S2 of the Argon. There's physics motivations, experimental physics motivations to push the Argon detectors toward trying to better resolve very low energy signals. One of those pointing to dark matter is light with dark matter detection. Much of the game in light with dark matter, as you probably know, is about extending the threshold of the detector to lower and lower energies. And there are many more events that happen at these low energies. And therefore, even a small improvement in the threshold makes for a great improvement in the kind of limit and sensitivity of the machine. And it's going to be especially important for ionization-only measurements, which many experiments are considering. Another great motivation is the recently observed Sevens channel, which is allows for a lot of new neutrino experiments to be performed, but all of these through the Sevens channel are going to result in very low energy recoils, sort of KeV and maybe even a bit lower energy recoils. And those will be difficult to perceive. And so we will need to push the threshold as low as possible to get at that. And then an interesting application of that is the possibility of monitoring nuclear reactors by observing their antineutrinos through the Sevens channel. There's a great abundance of signal there, but again, it's a very low energy signal that has to be seen. There are also some enabling technologies that make it fruitful to pursue this low energy improvement in liquid argon. One of those is the development of an argon source that will provide argon-39 depleted material. That material is extracted from underground gas in Colorado, and then it is going to be distilled in this very long cryogenic distillation column in Sardinia. And so we expect that there will be good material to use that is not going to have this unwanted background from argon-39 in it. And the other nice technical advance is there's been lots of progress recently in detecting vacuum ultraviolet light with SIPLMs. And these are a very nice replacement for PMTs, as I'm sure you've all heard. And you've also seen somewhat in talks from yesterday, and also there's numerous publications of people developing cryogenic amplification for these devices. Okay, to look a bit about how the chemistry works in improving the S2 light. So an electron that is drifted from the event of the ionization, that electron is extracted from the liquid surface and it is accelerated by the strong field toward the anode through the gas gap above the liquid surface. There it collides with whatever atoms are present, argon or xenon. And if it has sufficient energy above the threshold, there's an inelastic collision, it transfers the energy to an excited state of those atoms. First off, note that the threshold for that energy, the threshold for that excitation is lower for the xenon than for the argon. That's an immediate advantage because you'll get more xenon atoms excited than the argon atoms, and consequently more photons downstream. These atoms then go through a series of complex chemical reactions, which are roughly summarized in this package right here. And those chemical reactions lead to these exomer dimer molecules. Those dimer molecules then relax and release light at a characteristic time scale and a characteristic wavelength. If only argon is present, then you end up only with these argon dimers, and you end up with the light at the inconvenient 128 nanometers and the inconveniently long time scale. However, if you have some xenon around, then you produce more of this intermediate dimer, the mixed heteronuclear dimer, and you produce this much longer wavelength and probably, though we don't actually know yet, a much faster time scale for the light release. Finally, if you have lots of xenon around, you will eventually shift the light entirely toward this longest wavelength with the fastest time scale. The time scale is important because reducing the duration of the S2 light allows for a shorter integration window when any signal is analyzed. And that means that there is less opportunity for an unwanted integration of some background event. Here's how it looks in practice. This is a relatively old experiment. It's with a gas proportional counter. It's room temperature, 1 atmosphere. It starts at the top with pure argon, and then it's slowly adding xenon as we go from the top down. You can see this nice emission curve just showing the 128 nanometer light for the argon. As the xenon is added, that curve is extinguished and shifted over toward the intermediate signal at 147 nanometers. And so what this suggests to us is that if we add about 50 parts per million of xenon to the gas mixture where the S2 is occurring, we will successfully shift most of the energy out of the inconvenient wavelength and toward the longer wavelength. So that's our target. That's the number to keep in mind, 50 parts per million of xenon in the gas. Okay, what is that going to get us if we succeed in shifting that wavelength from 128 nanometers to 147? And so this is some material from Hamamatsu describing the sipping performance. And as you can see, there's a great improvement going up about 60% in quantum efficiency from this change. If we further shift from 147 to the longer 178 nanometer line, there's basically no further improvement. So getting it to 147 really does get the job done. All right, I've mentioned the 3 improvements so far: the longer wavelength and the faster time scale of the S2 light, and also that by the virtue of the lower threshold for excitation, we'll probably get more S2 photons per extracted electron. There's 2 other improvements that may occur by doping xenon into the argon. These occur in the liquid, and that is the xenon in the liquid, just like in the gas, has a lower ionization energy threshold. And so we may end up with a larger ionization yield in the liquid that way. We may also end up with a larger ionization yield in the liquid because there's sufficient energy in the excited argon atom in the liquid to transfer by a pending process and fully ionize a xenon atom in the liquid, therefore releasing an additional drift electron. Okay, so now setting up an experiment to actually see if this nice story happens in practice. The concept of the experiment is very simple. It's the straightforward dual phase time projection chamber that you're all familiar with. And then you simply observe the S2 and slowly add xenon to this mix and observe the S2 improve as you are adding xenon. And finally, you will reach a point where you can no longer add any xenon to the liquid mixture. And the key questions in doing this experiment, one is, how does the xenon partition between the liquid and the gas? And so that is that when the system is at thermal equilibrium, the rate of xenon evaporating from the liquid into the gas will equal the rate of xenon condensing from the gas into the liquid. So those rates will be matched across that surface. But in thermal equilibrium, the concentrations will not be equal in the gas phase versus the liquid phase. The concentration, in fact, in the liquid will be much, much greater. And this difference is determined by what's called the Henry's law constant. And we've estimated that to be about 330. And so most of the xenon is going to prefer the liquid phase versus the gas phase. And so in order to get the 50 part per million target we want in the xenon, we're going to have to add quite a lot of xenon. We'll be up to about 1.6% in the liquid. And the second question is, well, how much xenon can you actually put into the liquid? And in that case, there is direct experimental results, and we can just draw on that, fortunately. And we can place about 7% of xenon into the liquid. And if you go beyond 7%, then what happens is you start forming solid xenon, both inside of the liquid and inside of the gas rays. And once you get to the formation of solid xenon, further adding xenon doesn't help you, it just grows the solid xenon crystals. But anyway, it looks like we have about a factor of 4 to work with in terms of the solubility limit. And how we implement the experiment more in practice. The gas is drawn out of the main detector bath for return to the circulation and cleaning system. It's drawn right off the top of the bath, which means that the evaporation of the mixture occurs on the main detector surface. That evaporation, because of the large Henry's law constant, is essentially distilling the mixture. So even though the mixture here is at 1.6%, what is drawn off and going out through the circulation system is at this lower concentration of about 50 parts per million. That gas leaves, gets cleaned, and returns. It returns to our heat exchanger shown on the left. It's also allowed to directly go into the heat exchanger. The heat exchanger on the left is cooled in the center by a thermosyphon loop. And the thermosyphon loop can be loaded by nitrogen or argon, which is separate from the circulating material that I'm showing here. And so then the heat exchanger is fed only by gas, which has the low 50 parts per million xenon concentration. Both this path and this path have low xenon concentration. And therefore, just by concentration of xenon, once this condenses, the liquid inside of the heat exchanger is very much depleted in xenon, something like 50 parts per million, relative to the liquid in the main bath. And that is a great advantage because by running the heat exchanger in a very depleted mode, we greatly reduce the chance of having any xenon solidify on the cold structures of the central thermosyphon. Let me go back. I also wanted to show that we will also use thermosyphon cooling at the top of the detector. That's the top flange right here. And the point of that is to avoid unwanted heating and boiling of the liquid at the surface right here, where the vessel wall meets the liquid surface. And so we're trying to keep this very thermally neutral by making the can rather homogeneous in temperature.
Ethan, you have 2 minutes more.
Thank you very much. I'm almost done. So somewhat implementing the design here. There's a cryo cooler at the top, which is condensing the mixture for the thermosyphon. That liquid then cascades. There's an upper stage of the thermosyphon that cools the top of the detector. And then there's a lower stage of the thermosyphon that is inside of the heat exchanger for cooling the argon, which is condensing. Here's the hardware actually put together. I'll note that that intermediate level of the thermosyphon, we haven't constructed that yet, but otherwise it is what we planned. And then finally, the detector is made in such a way that it has a nice path going through that is open for neutron scattering experiments. So there's a low obstruction path. The whole detector is about 5 feet tall. And my last slide is just to show you the results of our first cool down. It's actually, we've done 2 cool downs now, and it behaves very much as we intended. And so here you can just see the kind of cascade of cooling on the upper left graph. The thermosyphon gets cooled at the top almost immediately when we turn on our helium cryocooler. That is starts condensing the thermosyphon gas. That's cooling the heat exchanger. That's in the green curve there. And then the heat exchanger is subsequently cooling the argon inside of the heat exchanger, and that's cooling the detector off right here. And on the right is just showing the stability of the system. As we go through a bunch of different control points, we're able to step in pressure to different pressure set points, and then feedback to our heaters is causing the system to correctly follow in a very nice stable way. And we're able to get our heat exchanger to transfer all of the liquid all of the heat that we need it to transfer. And so the first use of this, you've actually already seen that material, and that is that we just use it for argon alone. We flooded the detector with argon, and we had 3 SIPMs submerged in pure argon. And that result was discussed in Teal Pershing's talk yesterday, which is online, and you can review it if you like. And as for xenon doping, we haven't done it yet, but we are getting very close to trying it. That's what I have. Thank you.
Thank you. We are about time, but I don't know. It's up to yeah.
Let's have a question. We have 2 questions. Yeah.
Okay, so Lear.
We cannot hear you.
Can you hear me now?
Yes.
Okay, apologies. Anyhow, so thank you for the interesting talk. I'm wondering if you know something about the expected uniformity of the dissolved xenon inside the liquid argon.
We don't know that yet, except I will say that that is something we worry about. And so we are designing our system to encourage convection as much as possible. And so both the heat exchange part and especially the detector will be essentially fed by cold gas on one, a cold liquid on one side and heated on the other side with the intention of setting up the circulation loop. And we've also done some quantitative work on how this evaporation process results in the evaporation by the distillation that concentrates the xenon at the surface. But it looks like that will mix in just fine with the rest. So I don't think there's going to be too much of a concentration issue.
Christoph?
Yes, thank you. I was wondering about the Henry coefficient. So you said you estimated it. Can you elaborate on how this works?
I can, yes. Okay, so that's down here. So the basic, this is, you can think of this as the experiment that we're doing in terms of we're adding more and more xenon to the bath of liquid argon. So when you start out and you have the two-phase system, you have the argon in the bottom, argon gas in the top. When you're starting out adding xenon, the xenon is then partitioning just only between the gas and the liquid through evaporation and condensation, and no solid forms. And that's because the chemical potential of the solid is approximately constant as a function of the amount of xenon that's around. But the chemical potential of the xenon, that's proportional to the log of the pressure of the xenon. So it starts out very low when you only have a little bit of xenon. And then it grows as you increase the partial pressure of the xenon. And so as long as this partial pressure of the xenon in the liquid and the gas, as long as the chemical potential of the xenon in the liquid and the gas phase is lower than the solid phase, then you don't have any solid form. And you finally reach this point where they're matched. And once you get to that spot, then the solid starts to form. And then further addition, just the extra xenon material just runs out on the solid line because the material is always seeking the position of lowest chemical potential. Okay, so what you can do with that is you can take the experimental data, and this is the experimental data. It's quite old actually, but it's a very nice experiment. And that will tell you where you have saturation of the xenon in the argon. And it'll tell you that both the temperature and the pressure of that saturation point. And when you're at that saturation point, you have equal chemical potentials between all three phases, the solid phase, the gas phase, and the liquid phase. You have all of those three right at the solubility limit where they have equal chemical potentials. And when they have equal chemical potentials, you know something else, which is that you know that the density of the xenon in the gas is very much, is still determined by the ideal gas law applied to the xenon gas. And so you can actually just look up the pure xenon, you can look up the pure xenon vapor pressure, and you can apply that vapor pressure to the xenon in the mixture gas right here. And so that tells you how much xenon is in the gas, and the experiment tells you how much xenon is in the liquid, and then the ratio of those is the Henry's law value at the solubility limit. So you don't get to know Henry's law value on the curve, but you do get to know it right at the solubility. And I'm sorry if that was hard to follow. It was certainly difficult for us to figure out how to do it.
So this means that you put so much xenon inside until you reach solubility limit.
Yes, if that is the conceptual model that one uses to determine what the Henry's law constant is.
Okay, thanks.
But in our operation, we'll probably have about 1/4 of that value.
Okay, thank you. So let's